first, maybe the title of the topic sounds a little bit cryptic. But it is not. So what dynamic graphs are? They are indeed some kind of random graphs. Only they are created in a certain way. That's the reason why we call them dynamic. And as you probably all know, within graph theory, there is a famous Erdo-Shreni graph model. And Erdo-Shreni, in general, can be described with two parameters. With number of vertices t and the number p between 0 and 1, which describes the probability that for every pair of vertices, we draw independently a Bernoulli variable with probability p. And if it is the case that we put an edge between these two vertices, and we repeat that for all pairs. And such graphs are studied, well, for 60 years now, and they were studied extensively in terms of their structure, their behavior for different graph problems, such as coloring problems, independent set problems, and so on. But also they were studied in terms of classical graph properties like maximum degree of a given vertex. And moreover, they were studied in some context of entropy, which we'll talk later. But this is not the only random graph model. There are dozens of them. And what are dynamic graph models is probably the best expressed in another famous model, that is preferential attachment model. And in preferential attachment, we have the following situation. We have also two parameters, t and m, where t denotes the number of vertices, but the graph arises in following steps. We start from a certain graph on, let's say, t0 vertices. The simplest case, it is that that's the graph with one vertex and some amount of loops. Then, suppose we have graph on some t vertices. We attach a vertex with a label t plus 1. Then we do it in the following fashion. For every vertex, we have a degree. And of course, by assumption, the total sum of all degrees is equal to 2mt. So this is basically a scaling factor. And with that probability, we attach, we draw a vertex from, according to this distribution from this set. And we join these two vertices, if this is, for example, some v1. Then for m, we repeat this m times for a single vertex. And of course, the newly arrived vertex has degree m. It is connected. There is certain possibility that there are multiple edges to some vertices, but this is negligible in analysis most of the times. So we can assume with some asymptotic argument that the graph is basically simple. This model will become famous around year 2000. But there is also another model, which probably is longer than the preferential attachment model with us, but is less known. So it is basically, or maybe this is rather a family of models, not a model itself. We call it duplication divergence. And duplication divergence has also number of vertices, as these all have. Also has certain probability p associated with it, and possibly other parameters, and it all depends on the extensions. Suppose that this set is, in a basic version, the set of other parameters is empty, so we have only two parameters, and the graph arises like that. We start from a certain graph on t0 vertices, and again, we proceed iteratively. We add vertex t plus 1 in a way that we have t vertices in a graph. We pick a vertex uniformly at random. And we denote it as a parent vertex of t plus 1. Then a choice of a parent splits the whole graph into two parts, into the open neighborhood of the parent and the rest of the graph. So, of course, parent itself does not belong to the open neighborhood, but we have split into two sets. So maybe this set will be A1, this set will be A2, and we can join our new vertex to the rest of the graph. In the basic form, we did it as following. We take this vertex and we take separately each of these vertices, and we again draw a Bernoulli random variable with probability p. So this is how would we proceed if we were some kind of imitating Erdős-Rényi process only on this subset for this new vertex. And in basic version, we do not have any additional steps. So this model has some intuition from for example, the protein-protein interaction networks, that it is said that whenever we have such network, that new proteins arise in the following fashion, that some old protein mutates, and we have two distinct proteins. Of course, one is a mutation of the other, and this new protein somehow interacts more or less like this old protein. So it has more or less copied some of its neighbors. Of course, here we have this process is imperfect, since we know that the vertex of the new vertex always has a degree at most equal to the parent vertex. So there were certain ideas how to augment this model, and one of that we were certainly the most interested in is how to make this graph connected. So the main problem with this model in the theoretical analysis is that, as it turns out, if a vertex comes and by some chance it is isolated at some point in time, it remains isolated forever. And as it was shown that this number of these vertices grows actually asymptotically, that it is depending on the parameter p. Either almost all vertices are isolated, or a constant fraction of the graph is asymptotically isolated. So it is the large part, and we would like not to have such phenomenon arising, because when we translate it to the real world situation, we somehow need to deal with these isolated vertices, either to omit them in the analysis, or somehow to make the graph connected. One idea, which was done some years ago to make this graph somewhat connected, although it does not guarantee at all, it's to introduce another parameter r. And the parameter r basically says, okay, here we have drawn a variable with a distribution of Bernoulli of p. Let's say that, okay, there is some tiny chance that is equal to r over t for all the vertices outside the neighborhood of the parent. So here we have probability p, and here we have probability r over t. R over t guarantees that with high probability, we have around r neighbors in the rest of the graph. When r is like, I don't know, whenever we try to perform some fitting simulations, r was about 2, 3, and it was sufficient in most of the cases to generate a graph which was quite connected. So the number of the vertices which are isolated was pretty low. And of course, it complicates the whole process, because we do not have only the one set of Bernoulli variables, but also another set with another probability, which is changing. Okay, so what we can do with this model? We can do several things. First, what we can do is study the same as it was done for the Erdős-Rényi model, some kind of structural properties. And that's, for example, we can take any vertex S. And here I will, throughout the talk, I will label the vertices with numbers 1, 2, 3 up to t. So number denotes the time, the arrival time of the vertex. And we ask, what is the distribution of the degree? Of course, every model induces some probability distribution over graphs on T vertices. So this parameter is a random variable, and we ask about its distribution, how it behaves on average, what are the tails of this variable, and so on. Of course, this is only a preliminary step to get to something more, to get to the distribution of the maximum degree. And this is probably more interesting in terms of graph theoretic behavior, because if we knew all the distributions, then probably somehow we could easily bound the maximum degree. And of course, the lower bound, if we have any bound on that for any s, this gives us automatically a lower bound on this distribution. Okay, there are several other parameters that we can associate with but in this talk, I will mostly concentrate on that one as an example, because this is our main workhorse in the talk and in our work, and actually it allows us to go here. So another one from structural properties, what we can study is the parameter that is actually it's a phenomenon known as a power law. So we can ask as a value f of k. F of k would be actually f of k of t, let's say. And it would be the expected number of vertices such that degree of the vertex in T is equal exactly to k. So we ask what fraction of the vertices has degree exactly k. And if we know that the limit when k goes to infinity, when t goes to infinity, f of k behaves something like that, that it is known as a power law phenomena with the exponent alpha. So and it was shown that, for example, Erdős-Rényi does not exhibit this phenomenon, but preferential attachment, Bolobas shown in 2001 that for preferential attachment, it is the case that alpha equals 3. We on our side, and that will be the one part of our talk, that for duplication divergence, we can show that for certain range of parameters, it is indeed the case for alpha between 2 and 3. And it depends on the parameters of the model. So this we can study as structural properties. And these are the steps towards the next part, that is asymmetry and compression. And it was already the way which was proved for Erdős-Rényi for preferential attachment models, that if we know something about the distribution of the degrees, we can think, even if in some crude way, how to bound asymmetry and compression. So asymmetry in terms of the number of automorphisms, and of course it influences the compression. That if we take the graph, how well we can, so we have a space of graphs on T vertices, certain probability distribution over it, and we would try to write its binary representation that on average is as short as possible. Of course, since as with every probabilistic object, these we can bind from below using the entropy formula. So it would be minus some probability of G log, probability of G over all G drawn from that with the distribution. And it makes sense that, especially if we consider unlabeled graphs, then it has certain relation with the amount of symmetry that occurs in the graph. So it makes sense to look for the automorphisms. And it was shown for Erdős-Rényi and for preferential attachment. We have certain formulas and algorithms that both bound from below and provide algorithms which achieve that bound on entropy. So at least up to first 2 order terms, that we are certain that we have optimal algorithms which can compress these graphs. Okay, the third would be more practical stuff, and it is some kind of goodness of fit, that we have real world graphs and we try to somehow match them with models. Of course, this is hard because in practice we have, whenever we have a set of networks, they probably, if they were generated from this particular model, even under this assumption, probably every graph has some different set of parameters, and they all, we are not certain if they come from the middle range of the distribution or they are some kind of outliers. And there are many problematic cases, as with all goodness of fits. But of course, there is a certain way that we can proceed with our research. But I will spend most of the time talking about this and some of the time talking about this. Okay, so part one is how to deal with an average case. So we start by considering a simple problem that we have this parameter, degp of s, and we ask what's its mean value. And we can proceed iteratively, as it was done in the construction. That if we would like to find an expected value, then we can say what we can say about it. We can say that either in the vertex with number t+1 was connected to vertex number s or not. What is the probability of the first situation? So the probability of the first situation, that this vertex has this degree, it can occur under this general model dd t pr in two cases. Either this is an edge that was drawn with probability p, or it is an edge drawn with probability r over t. With probability p, if we were to draw this edge, so if there was a connection between t+1 and s, it has to be the case that parent is in the neighborhood of s. As this is symmetric, that s has to be in neighborhood of the parent. So this event happens with probability degree over t, and of course, it has to be the case that the event occurs. Similarly, if we have the other edge, then of course, the size of the non-neighborhood is equal to that, and we have an equation like this. And the latter part, what is the probability that the degree stays the same? Well, the simplest way to express it, it is 1 minus the same expression. Okay, so by simplification, we obtain eventually that this is like this. This is plus p over t minus r over t squared plus r over t. And this form is particularly important since it will repeat at some point in the future. So basically, what we have here is we have some sequence times, and here it is somewhat important that we have, in fact, two polynomials in terms of t, that we can express this as a division of two polynomials, and some remainder. Of course, there is an implicit dependency on the parameters of the model. And that solving that would be a way to achieve this. However, if we try to solve it iteratively, that we get that this is basically a product of I from s to t minus 1 of these quotients. And then we have a of s plus the same sum. Let's say it would be from s plus 1. No, it will be from s. Here will be j plus 1 t minus 1 And here will be again this division. So for this, we need a few things. First, this would be approximated for asymptotic purposes as an integral. And it would be no problem. In fact, what we did in the paper, it's much more that we get the constant here. I will concentrate on asymptotics because the constants are actually first pretty tough to get, and second pretty boring in terms of presentation. So I will spare you that. Second, we need to deal with this kind of products. And third, what we are missing, that somehow we need to get the starting point, and we are missing the starting point here. So how to get it? We start by considering what is degree T of T. Degree T of T comes, as with that process, as a sum of two binomial variables. So this is drawn from a binomial, and here first is what we draw from neighborhood of parent, and second what we draw from non-neighborhood. So here is okay. So I will write T plus 1 and T plus 1. So for simplicity, it would be T minus degree here, like that, and our R over T. So this is a sum of two binomial variables. It should be easy to handle. And if we try to compute the mean value, we can take a condition this on the value, on the degree of the parent, and we get a sum over all possible values from 0 to T minus 1. And this would be the average would be pk here, as this is an average of binomial, and here it would be T minus k over that. Right. Right. Okay. So what we get here is ultimately something. Yeah. And one thing that is missing, probability that degree of a parent of T plus 1 is equal to k. And here what we get, we have k times the probability of degree of the parent. But note that it only is a different way to express what is the average degree in the graph. If we take the sum of the vertices, we sum, and we denote it as dg of t. Actually, this is the expected value of that variable. So by this, we turn to this, and this actually turns out to be pretty simple. So we can count similarly as before. What we count here as an inductive step, that we can count all the endpoints of the edges. So in average, we have something like that, and that is then twice the number of edges in. So it should be here rather, T plus 1. Of course, these are all the edges that were before, plus twice the average degree of a new vertex. And interestingly, if we put these two together, we get a similar equation as here. The only difference is that it would be first the average value of gt. Here it would be 1 plus 2p minus 1 over t plus 1. So this one is slightly different. Here it would be 2r over t plus 1, and we would add 2r over t plus 1. So we notice that these are very similar, and the only difference is which polynomials are here and which polynomials are here. And how to handle it? Actually, handling is quite simple when you notice the fact that the products iterate one by one. And here, for example, whenever we have some product of from I equal s to t minus 1 over, let's say we take this one as an example. So this one is t squared plus pt minus r over t squared. And here we know that, okay, this equation, this part has two roots, which are in sum x1 and x2. They can be computed explicitly, but there is no need for that. And of course, here we have two roots equal to 0. It should be I or all over. Not to mess with that. Yep. Okay. But now it is the case that whenever we have a product from certain s to certain t plus 1, there goes a function which is an extension of a factorial function that is Euler gamma function, which is also defined for all the complex plane except some negative integers, if I remember. And this would be, this part would translate to these two. And of course, similar we have with the other. So we have something like this divided by something like this. And here we have s squared t squared. And from this, we can start proving asymptotics. And asymptotics, to get the constants, as I said, it was pretty tedious, but the simple fact that it is useful, that's whenever we have, let's say, something like that, so we divide these two values, then it is proportional to the t minus x1. So in general, whenever we have gamma of n plus a divided over gamma n plus b, so asymptotically it is proportional to n to the power a minus b. And from that, we get directly the asymptotics, whatever the t and s are. With handling of the constant is a bit harder, but it's still doable. So what we get from this? From this, since from here we get minus x1, here we get minus x2, and here we get minus x1 minus x2. What it gives us is that here we get t to the power minus x1 minus x2. However, this is p, right? Divided by the same s of p. So this is this product. And if we do this the same for these variables, here we have the same asymptotic result, only the difference now it is 2p minus 1. And of course, this directly translates to this because this is only a linear dependency. So all in all, here, oh, so maybe I will put it like that. That here, if we want to finally decide what this is equal to, for example, if s is constant, and we did it for all possible combination of s, but s constant is the most interesting part, this would be O of logarithm of t whenever p is equal to 0 and r is greater than 0, and t to the p otherwise. And this is just by studying this part. So this is how we how we did it in this case. And this was useful not only for its own sake, but actually the average case comes handy whenever we go to the studying of the large deviation, or how actually the variables can be far from the mean. And this is part 2. Okay, so I'll put it like that. And part 2 is what happens when we go far away from the mean. Or equivalently, we can ask whether the variable is concentrated or not. In this case, we supposed after some computer experiments that it is indeed concentrated. And moreover, we decided that we would look for the thing which is called with as a polynomial tail. So for certain, we look for the probability of degree of t of s being greater, or for some value which we do not yet know, to be expressible as a small o of t to the minus a. And there is we started for trying to derive that for explicitly for any a how what this value would be, but we ended with some more sloppy bounds that for all a greater than 0, such inequality holds, such asymptotic bound holds. And how did we do it? We started by considering, by splitting the whole sequence into steps. That of course we end at some point t, and we said like that okay, suppose that we have for vertices between 1 and t0, we have some good bound that we know that first we want to ensure that these vertices do not have large degrees, that we prove it only for s within this interval. Okay, how we do it? Suppose we start with some knowledge that, okay, here the degree is pretty small. Then let us think about some jump up to time t1, whether we can prove that within this jump, the degree cannot grow much. Okay, and let us repeat this process. Of course, this might not be perfect. And at some point, it might be the case that we jump over. Yet, we guarantee that these two are close enough, so we can approximate that, okay, let's say that t, even if we consider the degree of s at time tk, it won't be much further, it won't be too far from the t of s. Yeah, so okay, so we have a vertex, and we have some approximation on with high probability on deck t0 of s. Yep. And then we find it by using Chernow bound, and I will present it in a minute. How that given that knowledge, we prove that. So actually, even with that this difference cannot be high with high probability. And we iterate this process over all TIs. Actually, what we did is a bit more, that we approximated this difference, and we introduced another random variable xt. I will present a formula. Yeah, so it would be we bound it by some variable xt, and to prove the upper bound, we find xt which fits that, and xt has much nicer asymptotics to compute. So we know the asymptotics of that. Of course, the asymptotic, this is the upper bound on the latter part. And yeah, this is only for the beginning, for the vertices at the beginning. For later vertices, we had to do a trick which is quite lengthy, so I'll probably omitted that. But suppose that we have some vertex here, and we know that this vertex, so maybe not here, maybe here at some point, that we know that all these vertices have degree at most this one. And for each of these vertices, we assume, let's say that at this point in time, all vertices were bounded by by the degree which would be at this point. We know this with high probability. So we bound the starting degree, and then we prove that the degree of any given vertex within the interval cannot grow much as well. And with this, actually it's double induction. It's induction within the interval and then over the intervals. So it is quite tedious. Nevertheless, the main idea, I hope it's clear. Okay, so what did we do? Here, our starting point was a lemma which I could call Chernoff-like. So it actually uses Chernoff bound, but also uses a few assumptions. And let me, yeah. So suppose that we have certain values S and T. And in fact, taus would be such that they are TIs in our proof. So it would be only these given points in time. So this is the first assumption. The second assumption is that we have already starting condition like that, which would be, actually, it would be very simple. We would start at the starting point. We will assume that at T0, all vertices have degree at most T0, and T0 would be polylogarithmic. So it would be pretty small compared to the rest of the graph. In T, yeah, it would be log to the power of 4, if I remember correctly. But at least it is needed that T0 grows to infinity whenever T goes to infinity. So this was the harder part. Okay, so this is the second condition. Third condition is that we need H, which has two properties. First, for some epsilon between 0 and 1, it is less or equal than x of tau. And second, it has to be greater. So I will write it in asymptotic terms. It has to grow larger than, and here is easy to miss, that tau log t divided by epsilon, which is some constant. Okay, I will write it anyway. Px of tau plus r. And if we find that this interval is non-empty, and we find yeah, so this is, yeah, so this is basic asymptotic notation, so it has to grow faster in terms of t, because all these asymptotics is done in terms of t. Of course, tau would be here ti, so it would grow with t as well, and this would be constant, and this would grow with t as well. Okay. So suppose we have these four conditions, and this is the crucial lemma. So it would be a suitable random variable, which I will choose later. So I need to pick a certain xt, which actually would have good asymptotics that I can put here. And since it would be the upper bound on that, it will also give me an upper bound on the whole probability. Yep. Here, so here, suppose that xt grows like, I don't know, t to the p times polylog of t with high probability. Then I can put t to the p polylog here. Because I will guarantee that whenever it would hold over all the intervals, then but the definition is so general that it holds for every whenever only these are fulfilled. And this is actually tau plus h of s minus. And here it would be, this is 3 epsilon, but it comes actually here it would be 1 plus epsilon squared, only this is a sloppy bound on that. And it would be h p x tau plus r over t. And this is O of t to the minus a. And how did we do it? So we used the observation which was already before, only in a slightly different form. So suppose we have some one step, and we have okay, I will write it as an indicator variable. So this is of course indicator variable, meaning that whenever vertex S is connected to vertex tau plus I plus 1 or not. Okay, what is the distribution of this? This is clearly a Bernoulli variable. And it has distribution that's like that. In part 1, this is degree. Actually, it is the upper bound on that even. Plus r. So it probably should be minus some r over t squared, but it's an upper bound, and that's what we need. And then the question is, how do we? Oh, sorry, that's tau, and here is crucial thing: plus I, and we need somehow to get rid of these plus i's to get it nice. And we will do as following: that whenever we go with that, first we start by sloppy bounding the numerator. The denominator and the numerator would be bounded by another sloppy bound. Yeah. So at any point in time, it might grow at least at most by I. Okay. So second thing is that this we can bound by x tau. This, since we are within one interval, an interval is of length h, this we can bound like that. And this would be right. So it would be 1 plus h over x tau over t. And this is, by this assumption, 1 plus epsilon xt over t, x tau over tau. Okay, and whenever we have such independency, we know that this is stochastically dominated by this one. So we have p x tau plus r divided by tau. And for that, we have the random variables which are differences between these two, and we can use Chernoff bound. And Chernoff bound gives us the left part. Only thing that differs, that here we have 1 plus epsilon from the Chernoff bound itself, and another 1 plus epsilon, which I omitted here. So it is this one. So it is 1 plus epsilon squared, sloppy bounded, 1 plus 3 epsilon. And on the right side, we have something which is like exponent. So this is actually that. This is exponent of minus epsilon squared over 3. And here, this one, since we have here h variables which are differences, so h such variables, this is their mean. And here we also have their means, right? So we have h p of tau plus r plus 1 plus epsilon divided by, let me check. Yeah, of course. Here has to be tau. And the second bound gives us what we want. So the choice of H that guarantees that it holds. Okay, so we have these jumps. The only thing is to guess right X and prove its asymptotics, and prove that indeed we guessed X right in the way that this interval is non-empty, and this bound always holds. Okay, so how did we do it? Will it be visible? Probably, yeah. So how did we do it? We guessed. After a few tries, it worked. So now is the magic formula for the upper bound. For the lower bound, the proof goes similarly, only we start not at T0, which is a natural upper bound for the degree. We start at 1. And we need some assumptions to make sure that the graph is non-empty at the beginning of the process. But we have these two starting points, and then all in all, it grows like that. First, we have, this is Ti plus alpha Ti log Ti over xti, and this is xti plus beta log Ti, if I remember. Right. The first one is right. Second one is almost right, because we tried with constant beta. Unfortunately, it didn't work out. So we needed to variable, but the variable only on the second term. So it is constant plus something which is decreasing to 0. Okay, so we have that. And next few things are about the growth of X. So next lemma is whenever this is at least logarithm square, alpha is not too large, that is at most square root of phi, and beta I are greater than p minus delta for some, yeah, actually it holds for any, but then xti behaves at least like ti to the p minus delta. So this is very sloppy lower bound. Not that very. So from the average case, we know that for xt, we would expect t to the power of p. We only lose something at the exponent, something which is arbitrarily small, but we would like not to lose anything, or rather lose something polylogarithmic. Okay, so this we have the proof. It goes by induction, and the proof goes with a simplification that we denote it like that. And of course, the first step is obvious that this one has to be greater or equal than y of t0. Now, here, from now on, so this was working generally. This from now on will work, unfortunately, only for p, which is between 1/2 and 1. But we think that other cases could be treated similar fashion, that we have some sloppy bounds. We need to just tweak on them to prove that they are indeed polylogarithmic from the value that we want. So from t to the p. And here, whenever we have this, of course, this is for t0. this is T0 to the P. So so this bound holds. And this is, yeah. And actually, this is something like this. Okay, so what about the inductive step? The inductive step is okay. So we prove that this one is ti plus 1, which we can write like that. And for simplicity, I will denote it as h for now. So this is like that, minus ti p minus delta. Okay, and whenever we have something like that, what we can do, that we can put this out. Here we have 1 plus h over ti to this power minus 1. And here we use Taylor approximation. The cool part is that both we can show that this is between 0 and 1, and this is between 0 and 1. And as we all know that in this case, so I don't know, a few days ago I found it, one of my students didn't know it, so I consider it kind of obvious, but for especially for this bound holds, so we can bound it like that. Yep. For x and alpha between 0 and 1. Yeah, for alpha which is greater than 1, it does not hold because the second term is positive, and here fortunately it's negative. Yeah, when I was preparing the talk, I also had this second of doubt that wait, I should double check it. Fortunately, for in this case, it works, and here we substitute. Let me. Okay, for this we substitute it, and we get the proper bound that that this would be after these ti's will cancel out. So we would get something like this. And here it would be the case, that that this is nothing else that y ti. By induction assumption, this is less than xti. And they will cancel out. And we prove that the difference between them is less. Here, what would be, wait. I forgot this one. P minus delta. And we have only this part, and this part is less or equal than bi by this assumption, log ti. So we know that y is a lower bound on x. Okay, so we have this sloppy lower bound, and basically the proofs for the next case. So actually, what happens whenever we go slightly for slightly larger phi are similar. So they follow more or less the same technique. Only here we demand something stronger. That here we demand, unfortunately, that it has to be the case that this is between this and between something which is very tight. So this is alpha over 2 log ti. So unfortunately, we need to fit somewhere close to this bound. And first, when we tried, we had only this factor, and it couldn't work that way. So if this holds, then x of ti is less or equal than, whoa, 5 to 1 minus p ti to the p log ti. Log, yeah, only log. Okay, and again, we prove it by induction. This time by actually by subtracting one of from the other, and so we have ti plus 1 to the power of p log ti plus 1 minus xti plus 1. Okay, so xti plus 1 has very very nice formula, and here what we do, well, here what we do is we lose this factor at the beginning. So we have here we write ti to the p log ti. So we change this to this, but it's costless. And of course, we have ti plus 1 divided by ti to the power of p minus x of ti minus beta I log ti. And the trick is that we now take this. This is equal to 1 plus alpha log ti divided by xti to the power of p. Again, we hit the same range, right? So we again hit this. Or actually, no. In this case, we need lower bound on that. But lower bound on that is similar. We only need to consider 2. So this is, yeah. So we need to only consider 2 parts of the Taylor's approximation. And whenever we do like that, here what would turn out that the main part would be, okay, so this part with this one, which will come out. So this would be 1 plus p alpha log ti divided by xti minus some lower order terms. So the lower order would be p 1 minus p, if I remember, alpha squares, and that would be negligible since we have this bound. This grows like some ti to some power. This is logarithm square divided by this one. So obviously the in asymptotics it would vanish. And the only thing that remains is this part. And what's more, yeah. And I make a small cheat, because here what we use is that still this remains, but we also use this logarithm of ti plus 1 divided by logarithm of ti. And it also can be approximated in a similar way. So I won't torture you with that, but if we have these, then we need to write the upper part, and the upper part we was using, if I remember, something like this, and that was sufficient. And of course, ti plus 1 we expressed as the sum, and we we've taken out log ti out. So eventually, what we get this, so this part with this one canceled with this by induction assumption. And after all the dust settled, we got what we wanted. So we got basically that here it is this leading term log ti. Here it is alpha p plus alpha divided by log ti 1 minus something which is small order of 1 plus something which is of at least order log squared minus beta I log ti. Oh, yep. So I cheated. The induction canceled with this, not with this. And the trick is, whenever we have such formula, we need to make it greater or equal than 0. And whenever we fit within this interval below, then at some point, at least, this becomes greater, and that's the other part is negligible. So we use the asymptotics. We go with t as large as possible to get it. Okay, so that was the upper part, and actually it is sufficient now that observe that if we put all together, then we only need to find suitable phi and suitable epsilon. So finally, what we get is that whenever we get phi, which is logarithm to 4 of t, and then we have beta I, which is equal to this part. So it really fits on the right side of this interval. And alpha would be proportional to, alpha would be some complicated constant times log squared t. So it is, it has this property. Basically, it's all about this property, and alpha has to be large enough to work for these asymptotics. Then we can find h, which is appropriate to solve this problem, and we can use this Chernoff bound like to for the first vertices. So for all vertices up to log 4, we have this bound, and this bound basically says that that would be x of t would be log 5 minus 4p of t, and then here would be t to the p. Of course, in practice, it would be tk, and tk here, and we lose some, but we can drop it to t with losing some. Oh no, so upper bound works as well. So we are sure. I guess that if we were maybe ultimately, I guess that it can be bounded by 1 plus epsilon, adding that if we go here with t's, then we can go here. I guess we need to give k minus 1, and then prove that the latter part cannot be that much. So even the distance between tk minus 1 and tk is small, that even if we add the whole distance between them, it is negligible. Okay, so this is the upper bound. In the same fashion, we can prove the lower bound. So it is as tedious probably as you can imagine, but we can prove the good news is that when we all combine it together. So back to this picture, we have a lower bound for any vertex gives us the lower bound for the maximum degree, and that's great. So we have the upper bound for this gives us only an upper bound for these parts. But by double induction, by taking vertices within the interval, we can pursue this interval up and up, and we can prove that this indeed holds for all s's. And if this holds for all s's and for all a's, then of course the same holds for g to the t, because we can sum all of these events. So this is what we have. Of course, probably maybe choosing more suitable constants will give us better polylogs here, but at least it's polylogarithmic now, and it's not obvious at all how to get it by any other means. And whenever we have this, the question is how it can be used, because, for example, for preferential attachment, the maximum degree was used in a very ingenuine actually fashion to compute the symmetry and the entropy. So it gives us certain relation between the vertices in the graph. So they prove, for example, that whenever we have two vertices of high degree, they cannot be in any automorphism. They cannot map onto each other because they have neighborhoods with different degrees. And this is the trick they used. We hope that maybe some trick of that kind may be found in the future. Okay, so the last 10 minutes, I would talk about the last part, that is structural properties. So okay, actually here the trick is more analytic than here, but as you see, there are not too many drawings. Okay, where? Oh, it's here. Okay, so what we are interested in? We are interested in this quantity, and this quantity says how many vertices of degree k are in the graph. Unfortunately, there was a theorem back in, I don't know, 2005 or so by Hermann, who proved that, okay, let me denote by fk, a limit with t going to infinity of fk of t. He proved that fk is equal to 1 for k0 and 0 for otherwise. So actually, it's not entirely true. So this is some constant depending on p, and this constant is 1 whenever p is small enough, whenever it is below a certain threshold, and it is non-zero, but it is less than 1 whenever this is greater than this threshold. Intuitively, it makes sense. So whenever graph is sparse, then we expect that the isolated vertices would proliferate, because either we can copy isolated vertex and it would be isolated. And this is, yeah, this one is for r equals 0. So we do not add any additional edges, and the isolated vertices would proliferate. Whenever p is larger, then of course it would be much harder to get it. And here, I guess it is hard to get any reasonable bound on the latter part. In general, it was proved only that this is in standard asymptotic notation. That whenever we have like this is some kind of logarithmic bound. F1 here. So vertices with degree 1, there are at least logarithmic number of them, but nothing more is known. And we know that we do not have a linear number of that, and there's a huge gap. But on the other hand, what Hermann started and then was continued by Jordan, they did an interesting trick. In fact, they took the graph and they said, okay, this is a discrete dynamic process. Let's turn it to continuous time. And the second trick they did is they said, okay, let's not look at the given vertex. So let's not generate the graph and then draw the vertices uniformly at random. But let's do the following trick. Let's observe tracked vertex. Let's suppose that we have a graph on T0 vertices. We choose one vertex. And we observe the degree of that vertex until it was chosen as a parent of some new vertex. Then we jump to observing this vertex. And then, if this vertex was copied at some later point in time, then we jump to its copy, and so on and so on. And by this, we generate a process. This, of course, this can be also formulated in some discrete setting, but we can also have a continuous time Markov process that describes degree of these vertices. It turns out, and they prove it, so actually, if I remember, that was proved by Jordan, then these two processes are equivalent. That is that if we go with time to infinity, the probability of hitting, so I will denote it, but probability of that by choosing uniform a vertex from T vertices. Okay, so let U be the degree of that vertex chosen uniformly, that K to the probability of this tracked vertex approach degree, it goes to 1. So in fact, in this setting, it doesn't matter which method do we choose and why Jordan chose this, because this way, this tracked vertex allows us to formulate a generator for for continuous time Markov process. So we have a generator Q, and it is written as as following: that we have only a few transitions. So this matrix is quite sparse. Oh, in fact, it has only lower diagonal and one line over it. And we ask the questions, what are the probabilities? And probabilities here, the continuous time embedding gives us independency of n, which was in T, which was a problem here because dependency of T arrives. And here, by doing this trick, they made it to get rid of T. And here, the probability, so the probability is like that. So it is basically the binomial probability that we, from a vertex which has degree j, we generate a vertex which has degree k. And this goes for all k between 0 and j minus 1. This goes jp. So this means that we have a vertex of degree j, and it got an additional edge. So it was a neighbor of one of j vertices. So one of its j neighbors was chosen as a parent of a new vertex. And here, because it has sum up to 0, actually, in continuous case, so it has to be minus jp minus 1 minus p to the j. Okay, so this goes like that. Then the next trick. Next trick was, okay, consider this is a generator matrix. So let's consider a left eigenvalue, and we know it is non-negative. And here, in fact, they made a trick which was the theorem. Actually, I barely understood it, but the trick was that we do not need to take a whole matrix Q, because with the whole matrix Q, it is the problem that 0 is an absorbing state. And actually, they showed a theorem, which still I don't believe, but it was published somehow and it was back in the 80s, and which says that we can take any submatrix provided that it has certain properties, and they just get rid of the first row and first column. So they are not asking about f of k, they are asking about a of k, which is f of k divided by 1 minus f0. And q here is with this small annotation that this is matrix q, but without first row and without first column. Okay, so from that, we can get a set of equations. And this set of equations actually allow us to compute generating functions. And what Alder Jordan gave us, so he proved a lot, but what he gave us as a tool, that he gave us a generating function, and that's what we like the most. And his generating function was, of course, generating function was for that AK, and it was a to the pz plus 1 minus p, which is equal to p az plus some constant. Let me okay, pz 1 minus z a prime of z plus a 1 minus p, and this is some constant. Of course, a here is a generating function of a of k, so a of z is a sum of all akz to the k. Here for actually starting from 1, and he, using his own methods, proved that it can be shown from this that az behaves in such a way that we can show that whenever we go with ak, it grows asymptotically larger than k to the minus b minus epsilon for some constant b, probably the other way around, and greater than minus b plus epsilon weight minus 2 minus 3. I guess I get it right in the first place. So he proved that asymptotically we are between these bounds. We actually, what we did, we closed this. So we've shown that we found the constant, which is a very elaborate expression, and we found that it is indeed k to minus b minus beta, and how it can be done. So the brief outline would be like that. I don't know how many of you are familiar with Mellin transform, and Mellin transform turns out to be a very useful tool in the area of analytic combinatorics. So probably most of you have written one time or another Fourier transform. And Fourier transform is defined formally as an integral from, I don't know, from minus infinity to plus infinity. Mellin transform is similar in the sense that it can be written as also as an integral of, I never remember the exact formula. F U D S. Yeah. It was okay. dw, w and w, and this is the nice thing. The nice thing about that is that S. Yeah, thank you. Nice thing about that is that we can translate it. So this form actually does not work well, but no, we did two substitutions, and one substitution is that we took z and we replaced it by 1 minus v, and the other substitution is that we took v and replaced it by 1 over w. And we also made the similar substitutions for functions because it was easier to work that way. So it's symmetric, actually, fortunately. And it turns out that we got something like this, that we got, here is w over p, here is 2p c to the w, here it changed a bit, so this is pw minus 1 c prime of w plus some constant, right? So here we can leave it like that. And we know a few things about this function. That first, we know that c of 1 is equal to a of 0, and a of 0 is just 0. That's a simple fact directly from the definition of this function. Next, we know c of infinity, which is actually whenever it is plus infinity, then of course it is a of 1, and this is by definition of the generating function. Since this is a generating function of some probability distribution, it cannot exceed 1. So there can be cases that, since these are all limits, it can be degenerate, but it is definitely some constant between 0 and 1. Okay, so Mellin transform has a few nice properties. Unfortunately, it requires that we know how it behaves around 0 and infinity. Infinity we have, 0 we don't. So what we did, we introduced an auxiliary function which is exactly the same as this, only it has plus k. It has different constant, and we assumed that it has a Mellin transform in certain fundamental strip. So if you don't recall, this is the hard part of Mellin transform, that in the fact of every inverse transform, that it can be expressed as an integral over some over some line which is parallel to the imaginary axis. This was the definition. That's I know that's but that's the problem with going this part of exposition too deep. Actually, it goes like that. That if we have these parts, then we can apply Mellin transform. And what we did, we suppose that this formula exists for some k. And of course, if the formula exists for some k, which may not be equal to this one, the solution for C is just a matter of linear scaling. So let's assume, for the sake of discussion, that here is a k. And of course, the asymptotics of C, whenever we have some constant k with some different constant, would be the same. Okay, so when we use Mellin transform, it has very nice properties, since it gave us, if I'm not mistaken, what it does, that if we have such formula, then here p minus s, and here is s as well, goes out. And this nice property gives us this. Here we have to split it into two parts, but the first one is, if I remember, p to the s c star s, and unfortunately here we have p c star s minus 1, and this vanishes. This only determines how we invert the Mellin transform. And okay, and what we did was basically we solved this this equation. We obtained a product which was quite convoluted, but so eventually it turned out that it was, let me double check. Where d to the s, unfortunately, does not have the nice, so it is a product, but it does not have quite nice expression. So it is product from 0 to infinity, and it is 1 plus p 1 plus j minus s minus j minus 2. Okay, and the crucial thing is that when we invert, I said that it is okay, so I probably would need that part of as for the last one, when we invert, what it matters actually the location of the residues of the function. So I told you that we do integration over a line to invert it. But the crucial part is how to locate the poles of this function. And fortunately, gamma of s has poles in 0, -1, -2, -3, and so on. P to some power does not have any poles, and d of s has a series of poles twofold. First, it has poles in 1, 2, 3, 4, and so on. Next, it has poles in some values which are slightly larger than 1, slightly larger than 2, and so on. And as you see, since this is a product, and this is only shifted by 1 at each point, that all solutions, if we find fundamental solutions here, then all other solutions are just shifted by 1 in this direction. Okay, so what we do? Basically, we established by some argument that fundamental strip is between -1 and 0. So we need to integrate over this line. And the trick is now like that. Main transform has this nice property, which is called smallness property. How do we integrate over this line? Sometimes it is hard. Actually, here we know that this function behaves well. Why? We proved, although this is the argument that we put to the appendix because it was so technical, that 1 over the absolute value of d of s is absolutely convergent. So, so this is bounded by some constant. This does not grow more than exponent s log s. So this basically can kill any part of this. And by this, we established that this behaves well. Moreover, this behaves well if we have the real value fixed. So if we go with imaginary part to the plus minus infinity, this behaves well, this decreases double exponentially, and all is well. Okay, so whenever we want to compute an inverse transform, which is whenever we go c to the w is equal, this is some scaling factor. Here we need some part that is equal to c. C, by the argument that I will omit, that it's chosen between -1 and 0. And here it would be c star of s. Let me, the inverse was like, yep. Yeah. Yes. Okay, so the trick is that we can approximate it by some rectangle. Rectangle has, which has two nice properties. That first, the smallest property, and this is general property of Mellin transform, whenever we go with these both to plus minus infinity, by these conditions that by good behavior of both these functions, it is negligible. So we can bound it by any polynomial. And the second part, whenever we go with this, if we stop at any point m, that good behavior gives us that what counts here counts as w to the minus m. So we can make any small as we like. And the third nice thing is that an integral over some rectangle is equal to the sum of the residues at these points. And bottom line, we have residues at 0, 1, and 2. And the funny part, whenever we go with the formula, we obtained that c to the w is equal to some constant times w to minus 0. So this won't be here. W to minus 1 plus w to minus 2 plus w to minus s star plus 1 plus some asymptotics of s star plus 2. Whenever we go to a and z, here all of these becomes 1 minus z to the power of 1, to the power of 2, to the power of this. If these are integers, these are polynomials, this does not count to the asymptotics. So the asymptotics is dominated by this. And this, whenever we try to count this part, this would be proportional to the k to minus s. And here we need to, if I remember, subtract 2, because it would be -1, -2, if I remember. Yeah. And s is between 0 and 1. And this is why the exponent is between 2 and 3. So, okay, so that was all I prepared. I know that's it's a lot, and last part I did rabbit jumps over, but I hope that at least the outline of what I was talking was at some point understandable. Thank you.